These are the frequently asked questions for Algebra 2 for section 6.3, day 1. I'm going to start with number 16 here. And number 16 says the design of a garden path uses stone pieces shaped as squares, and we can see them over there, but I want to have a drawing a little square here, in case you're struggling with this one. And these are shaped as squares with a side length of 15 inches, so we have 15 on each one of these. And I notice that what's going on here for these side lengths is really the diagonal of this figure. And they want us to find the length of the path. So to do that, I'm going to need to know how much that diagonal is. And that gives me the realization that I have formed a 45, 45, 90 triangle. And so I'd sing a little song, 30, 60, and 90. It's very easy to see. The short side is 1, the hypotenuse 2. The other side is the square root of 3, and it's 45, 45, 90. These are easy to name, for it's 1, 1, square root of 2 in the triangle game. So I need the 45, 45, 90 triangle over here, and the relationship between those side lengths is you take the leg, which is in this case 1, but it could just be x, and you multiply it by the square root of 2 to get the hypotenuse. So if these sides were 15, this diagonal is 15 square roots of 2. And I just need to count up how many of those I need for the length of this path. And right here I see that I have basically a half of one, but you know what, I've got another half at the end, so that's going to work out nicely. So we have 1, 2, 3, 4, 5, and then 2 halves put together. So we have 6 of these 15 square roots of 2. So we would take 6 times 15 and get 90 square roots of 2. And then this, of course, they probably want you to get a decimal so that you could tell them what that would be approximately. So 90 times the square root of 2 comes out to about 127.3, and this was in inches. So for this one we didn't need the whole perimeter, we just needed the length. The ones we did in class actually were more involved because we had to get the perimeter for those. Then, let's see, number 21 was another one I wanted to go through with you. And what we generally do with these is, first of all, we look and notice they're both cube roots, and that's great because we need these to be cube roots. And then what I'll start doing is I'll start with the smaller of the two. And so I have the cubed root of 54, and I know that's the cubed root of 27 and the cubed root of 2. Well, that's going to be negative 2 times 3 cubed roots of 2, which is negative 6 cubed roots of 2. Now, the reason I didn't do the front yet is because if we're going to be able to do the subtraction, then that cubed root of 81 has to split into the cubed root of 2 because we can only add or subtract cubed roots of 2 to other cubed roots of 2. But I noticed right away that's not going to happen because 81 divided by 2 is 40.5. That is not a perfect cube. So not going to work this time. We can still simplify them, but we're not going to be able to go ahead and do that subtraction. So I think about my cubed root of 81, and I have 3, and I realize 27 will go into 81 3 times. So this will be the cubed root of 27 and the cubed root of 3 when we break that down. So that will give us 3 times 3 cubed roots of 3, and that will be 9 cubed roots of 3. So our answer to this is 9 cubed roots of 3 minus 6 cubed roots of 2. There is nothing else we can do with that. You cannot do the subtraction unless you have like radicals, and those are not like radicals. So we break those apart and check to see if we can actually do the addition and subtraction. Then number 75 was one I thought perhaps you might struggle a little bit with if you go about this the wrong way. The first thing that I'm going to do is I'm going to change that 0.5x to 1/2. And what I want to investigate is how does that make this problem more difficult? Well, because we have 4 divided by 1/2, and we can do that math. That comes out to 8. So 4 divided by 1/2 is really 4 times 2 over 1, which gives you 8. So now if we split this up, this actually doesn't look too bad. We get 2 over the cubed root of x. But of course, oops, pardon me, dropped my eraser there. We know we're not done because we have a radical in the denominator, but boy did we make that a lot simpler just by noticing 4 divided by 1/2 is 8. So now what I want to do is I want to get rid of that radical in the denominator. To do that, my index for my radical must match my power. And I had an x to the first. So 3 doesn't go into 1. But if I take x to the first times x squared, I'll have x to the third. And that is going to help out a lot. So that will give me the cubed root of x to the third, which is of course just x. And my numerator just comes along for the ride as I go through that. Again, it's always that focus on the denominator, but for this problem especially, you want to notice that right away, that 4 divided by 1/2 is 8. Makes the problem so much easier. All right, let's look at 78. 78, we have the cubed root of 2x squared times the cubed root of 4x. And I'm thinking, you know what, I better put those together and see what I have because they're both cube roots. I can go ahead and do that multiplication. 4 times 2 is 8. Fabulous, for the reason we just had in the last problem. X squared times x to the first, you add the exponents. Even better, because when we do the cubed root of 8, that's going to give us 2. And when we do the cubed root of x cubed, that's going to give us x. So here's 2x. Now last but not least, we check to see if we need any absolute value bars. Both of these problems had cubed roots, and cubed roots, you can have negatives. So we don't need any absolute value bars for these two problems. Number 79, I'm going to do a little erasing here. All right, so 79. Again, I have 2 square roots and I need to multiply, so I can go ahead and do that multiplication because I have square roots here. So what I need to do is a little 14 times 7, which gives me 98. And then x to the first and x to the third, when we multiply similar bases, we add the exponents. So now I'm looking for the square root of 98 and the square root of x to the fourth. Well, 98 feels really suspicious. So I remember, hey, that's going to be 49 and 2. So that'll be the square root of 49, square root of 2, and then the square root of x to the fourth. Remember, we just take the 4 and divide it by the index, which is 2, and that will give us x squared. So this will be 7 square roots of 2, x squared, which we'll write as 7x squared square roots of 2. Now this was a square root, and originally the author definitely wanted things to come out positive, but we ended up with an even power down here anyway, so we don't need absolute value bars. But that's something we still have to watch out for. Whenever we have variables, we have to think about the intent of the person that wrote the problem. Then number 80, we have the square root of 3x times the square root of 5x, and that will of course give us the square root of 15x squared. So we need the square root of 15 and we need the square root of x squared. The square root of 15, we do not have any perfect squares that go into that, but we certainly do know the square root of x squared is x. So this will be x square roots of 15. Now we go back to the original problem to figure out whether or not we're going to need absolute value bars. And we notice that the author of this problem left that so that if somebody put negatives in, they'd just get no real solutions. So that means we don't have to worry about it. If they had even powers up there and we came out with our odd answer, we'd have to put some absolute value bars there, but we do not. That did not work out this time. Then, let me see if I can squish 81 in here. All right, now, 81. You take a look at that one and you think, oh, let's just go ahead and multiply those two together. I'm not going to. I'm going to simplify them first. Those are nice perfect squares up there. the square root of 9x squared is 3x. And the square root of 25x squared is 5x. The answer to this is 15x squared. So again, always be thinking, is there an easier way to do this problem? And then in this case, again, we ended up with x squared, so there isn't any way that that would come out negative anyway, but we always check. So there we have it. That should do it for this assignment.